All right, so in the last unit that we looked at motion and how things move. Now we're going to look at kind of why things move, and that is forces, which involves Newton's three laws. And again, this is kind of review from grade 11, except for, again, we're going to be adding dimensions. All right, so we'll just, I'm going to briefly go over Newton's three laws because I am going to more in-depth go over them as we go through some examples here. All right, so the first law, Newton's first law, is if your net force is zero, then your acceleration is zero. Now, from our motion unit, when your acceleration is zero, it means your velocity is not changing. So that means your object is going to either stay at rest or it's going to keep moving at the same velocity that it was already moving at. So the acceleration means no change in velocity, whether you're already moving or you're not moving. The second law for Newton's law is kind of simple because all it is a formula, is that your net force is equal to mass times acceleration. So you can see again, our net force is a vector, which means it has magnitude and direction. But our mass, of course, no arrow there because you cannot have direction on your mass. Although you might feel that way, that it's going up or going down, depending on how things are going for you. Third law is that for every force, there is a reaction force, which is equal in size, but yet opposite in direction. So again, we're going to go through these laws in terms of some examples. All right, so on that note, or on this note, I should say, example number one, where we're looking at, again, just reading off my sheet here, a golfer hits a golf ball with an average force of 15 newtons at 20 degrees above the horizontal. Of course, the force of gravity is working on the golf ball, and that is at 0.9 newtons. Calculate the net force, because you can see in a lot of these laws, it's all about the net force. Calculate the net force on the ball at the moment of impact, assuming zero air resistance. All right, so no air resistance is going on. Want to find the net force acting on this golf ball. All right, so this golf ball is being hit. So I'm going to draw a horizontal here, which is my ground. All right, and our golf ball is being, there it is, being shot up. It has a force of 15 newtons acting on it. All right, and the angle that it is being launched at is 20 degrees above the horizontal. Again, there's our dotted line, there's our horizontal, and we want to figure out what our net force is. Now, we also have the force of gravity, which is 0.9 newtons, and of course, down. All right, so what I'm going to do is, and this is something that we've done with a lot, is that I'm going to break down the original force into components. So of course I'm going to use trigonometry, which I know some of you are fans of and some of you are not. All right, so I'm going to call this force, let's see here, the applied force. That's a name used quite a bit, so that's going to be called F of A. And so horizontally, I've got F of AH. I'll make sure I use the same notation as my note. And vertically, I have F of A, but vertical. So F of AV. Again, just notation stuff. So again, just like I did before, when I'm breaking a vector down into components, whether it's a velocity or a force, I'm going to use the same method. All right, so let's find my vertical here first. So it is opposite of the 20-degree angle. Again, we're with vectors. We're always going to have the hypotenuse. So I'm looking at sine 20 degrees is equal to that FAV, FAV divided by the 15. Let's see, rearrange that. So FAV, again, I'm having fraction equaling a fraction. Let's see here. So I got 15 times sine 20 degrees. And whoops, FAV. Do a little bit of calculations there. So I got 15 times the sine of 20 degrees. And I'm getting 5.19 newtons. And again, it is, let me see, directed up. I hope so. Really wouldn't be a good golf shot if it was directed down. All right, now my vertical force here. Let's see here. So, my horizontal force. Again, it is the adjacent, so I'm going to use cos 20 degrees. All right, is equal to FAH divided by my hypotenuse, which is 15. Again, I can simplify that. I'm going to do it a little quicker because we've done so much of this. Again, I would have a fraction equaling a fraction, so 1 times that with that. Now I go 15 times cos 20. And 15 times cos 20 is 14.1 newtons. And our direction is, in this case, I'm just going to say to the right. All right, now, these are the 1, 2, 3 forces that are acting on the golf ball. These two combine to be our applied force. So really there's 2 forces. I just took 1 force and broke it up into 2 components. Now the best thing for us is that the gravity is already in component form because it is just straight down. So if I want to find my net force, I've got to add up all these forces. So I'm going to do the same thing I did before when we were talking about velocity. I put the vertical components together, I put the horizontal components together, and then I create the net vector, or in this case, F of net. All right, so first off, horizontally, I only have 1 force. I don't have to do anything here. Here's our net horizontal force. So I'm going to call that, I don't know, what did I use here? I guess our net force, there's a couple terminology here. I'm going to use F of R. Again, the R stands for resultant, the result of me putting these two together. All right, so this F of AH, because it is the only horizontal component, it's actually going to be my FRH also. All right, so that's 14.1 newtons. And again, I'm going to say it's to the right that this golf ball is being hit. But now I have to put my 2 vertical components together, my 5.19 newtons from the applied force and my gravity. And so when I look at that, running in the room here, let's see here. Put it right down here. All right, so F of R, but the vertical components. So I have a 5.19 up. I have a 0.9 down because they're in the opposite direction. Of course, I have to subtract them. And when I do, I get 4.29 newtons. It's a positive number. Or you could look at the fact that up was bigger than down. So in the end, we get 4.19 newtons up. All right, so I want my resultant force. So I've got my horizontal component of the resultant force, my vertical component of the resultant force. So I'm going to do exactly what I did before with velocity. I'm going to create a triangle, get my magnitude, and get my direction from that diagram. So here we go. Let's see. So we're going 14.1 newtons to the right. And then I got 4.29 newtons up. This resultant that I'm talking about, this F of R, it's going to be my nice green arrow here. That's my resultant or net force. All right, so again, I'm going to use, like as I mentioned, the Pythagorean theorem here. So I've got my F of R squared is equal to 4.29 squared plus this 14.1 squared. And if I use the old Pythagorean theorem, I end up with 14.64 newtons. And of course, I need the angle. So again, I have a triangle here. You have to be able to figure out what angle I'm actually looking for. Again, this horizontal line is the ground, so I'm going to find theta there. And of course, I'm going to use trigonometry where I have tan theta is equal to, let's see, I got my opposite, my adjacent, so 4.29 divided by 14.1. I get my theta to be, let me see here, 14 or 4.29 divided by 14.1, tan inverse. I get 17.04 degrees. Woo! All right. It's a good thing. This is all I got left. That's all I need. because now I've got my resultant force or my net force. My net force is equal to, there's the magnitude there, it's the 14.64 newtons. And the angle here is 17.04 degrees. You could say with the ground. I think your textbook often says with the horizontal or with the ground. Same thing. So 17.04 degrees with the ground. I'll go with ground this time because it fits. Horizontal is a little too big a word. And there we go. So again, we're applying the same concepts just to our same skills, just to a different concept. So we're adding vectors again, the same way we did with velocity, only now we're just using forces. All right, which gets us to our next example. And guess what? We're doing pretty much going to do the same thing. So let's see here. I'm going to need that space, so we'll get rid of that. All right, so next up, example 2. 2 people push on a broken 250 kilogram riding lawnmower. That sucks. That is facing north. If one person pushes the with a force of F1, which is 400 newtons, 35 degrees east of north, and the other pushes with a force of 800 newtons north, two double ends there, what is the acceleration of the riding lawnmower? All right, so I read the question. Here we go. I'm going to write down the information. So this is example 2 here. The mass is 250 kilograms. The first force that we have here is 400 newtons. All right, 35 degrees east of north. And our second force from the other person is 800 newtons north. All right, and we are looking for the acceleration. All right, now this comes down to Newton's second law, which is we have our mass, we have our forces. We don't have our net force yet, but we need our acceleration. And Newton's second law simply is a formula where F net is equal to m times a. All right, but the thing is we don't have F net yet, but we can find it. Your net force is actually defined as the sum of all forces. So we've got 2 of them here. There's no friction mentioned, so if something's not mentioned, it doesn't exist. So we don't. We have a perfect world in physics here. All right, so again, I got to add F1 and F2, just like I did before and just like I did with velocity vectors. All right, now I'm lucky here because look at F2, it's 800 newtons north. So we've already got a vertical component. It's strictly a vertical component. But I got to take F1 here and I got to break it down into its 2 components, vertical and horizontal. So I'm going to draw a little bit of a sketch over here of F1. All right, so we go never enter stinky washrooms. All right, our vector is in the northeast quadrant here, so I'll just draw a sketch again to do trig. It's 400 newtons, 35 degrees towards the east from the north. So there's our 35-degree angle there. All right, let's see here. So I go up and over, and so there is my F1V. And there's my F1H. And again, the magnitude of my vector is 400 newtons. So there's my magnitude. All right, so once again, I got to do some trig. All right, again, I'm going to go a little quicker because we've been doing this quite a bit. All right, so again, 35 degrees. So this time my horizontal is the opposite. So it's going to be 400 times sine 35 degrees. And my horizontal force, let me see here. I multiply 400 times sine 35. I get 229.5 0.43 newtons, and it is directed towards the east. All right, my vertical component of that first force, let's see here, I'm going to have it is the adjacent, so it is going to be 400 times, cos 35 degrees. And my F1V is going to be, let's see here, 400 times cos 35. I get 327.66 newtons. Again, looking at my diagram, it is headed to the north, so it's headed because it's headed up. So put an N there. All right, now, again, I need my net force here. I got to add these forces together, so I got to do that whole triangle thing again. All right, so draw my resultant or my net force. All right, so looks like I got to find out my components here. So first off, I only have one horizontal component. So my resultant, or my net force, but again, I'll call it my resultant, F of R, because writing F net and then throwing a H in there or V in there could be maybe confusing. I'm not sure. Let's see here. So my resultant horizontal component, well, there's only one of them, so it's going to be this 229.43. All right, newtons east. And my vertical of my resultant. Well, I have two verticals. I have this 327.66 going north, and I also have this 800 going north. So because they're in the same direction, I can add them. And so if I take those and I add them, I believe I get 1127.66. And again, they're in the same direction, which is north. All right, so now for my resultant, which again is my net force, I'm going to draw a triangle here. Right, so up I go, north of 1,127.66. Then I go over to the east, 229.43. All right, so there's north, east, south down here, west, just for reference. Our resultant, there it is. F of R, or again, could be F of net. Take your pick. All right, now, and I need this angle. So once again, I would use the Pythagorean theorem. Now I'm going to not go through the gory details here, but again, when I find my resultant, I use the Pythagorean theorem. I get 1,150.76 newtons. All right, so that is, again, using the Pythagorean theorem. Theta, again, tan, I would use opposite over adjacent. And so when I did my angle, I actually get 11.5 degrees. All right, now, what that means now is I'm going back into my original formula here that I need. F of net equals MA. Well, my net force, let's pick a different color here so it stands out. My net force here is 1,150.76 newtons. The angle is 11.5 degrees. Let's see here. East of north, because we're going towards the east from the north, so east of north. All right, and that's going to equal, let's get rid of this. I don't need this stuff now. All right, it's going to equal my mass times my acceleration. So my mass, I think I wrote it up here, 250. All right, so, well, to get A by itself, I'm going to divide both sides by my 250 kilograms. All right, so those divide each other out. And that means my A value, which we're looking for, the acceleration of this riding lawnmower, I take my 1,150.76, I divide it by 250, And I get 4.6 meters per second squared. And again, acceleration has direction. It would be my 11.5 degrees, that won't change, east of north. There we go. So again, same skills that we've been using. The only difference here is that we're just applying it to a different situation where we're dealing with forces, and so we're dealing with a different formula. All right, so again, just adding our vectors up. Now, we'll get to a little something different here in the last example, example 4. 4. All right, so example 4, 2 students, 80 kilograms and 50 kilograms, face each other sitting in rolling chairs. I often do this in class with the bottom of their feet touching each other. So they're both up on their chairs, they got their feet, and they push off of each other. And the larger student accelerates at a rate of 3 meters per second squared. What is the acceleration of the smaller student? Okay. Now, so I'm going to write down a few things here. My first student, who's that? I'm going to say that's the big one. So the mass of person A is 80 kilograms. The mass of person B here is, what is it, 50? Yeah, 50 kilograms. All right, so let's see here. We got our two people. The acceleration of person A is 3.0 meters per second squared. The acceleration of person B, we don't know. All right, now they push off each other. So A pushes on B and B pushes on A. So I might be drawing this a little bit different than the question I have. Now, when they push off each other, when B, and this comes down to Newton's third law, is that when you have a force, there is a reaction force that's equal in magnitude, but yet opposite in direction. And so when B pushes on A pushes back on B. And when A pushes on B, B pushes back on A. And the forces are equal. All right, so the force that they put on each other is equal, because as they're pushing on each other, you get a push back, a reaction force, equal in magnitude, opposite in direction. So in this case, the force on A is equal to the force on B, with one distinct difference. Well, we'll get to that actually. I'll get but a little negative sign, because they're opposite directions. So the forces are equal, but again, I put the minus sign there because, again, it's opposite direction. Again, that's because of Newton's third law. Now, again, there's Newton's second law, which we have is F equals ma. And so instead of having the force of A, I'm actually going to write that would be the mass of A times the acceleration of A. Put a little arrow there. And that's equal to the mass negative, whoops, forgot my minus sign here. Yep, there it is. We're talking about mass of B times the acceleration of B. Now, what I have to do here is, you see my acceleration here? I don't have any direction on it. So if A pushes on B and B pushes on A is going to go to the left and B is going to go to the right. So now this might be a little bit different than my note because of my diagram. So I'm going to say that A acceleration is left, which, as I've said many times, I count as negative. All right, now I'm going to substitute my values in here. And so what happens is the mass of A is 80. The acceleration is 3 meters per second left. So I'm going to put a minus 3 in there because, again, I always say left is negative, right is positive. I have this minus sign because, again, Newton's third law, equal in magnitude, opposite direction. The mass of B is 50. And we don't know the acceleration of the second person, the 50 kilogram person. All right, so now I'm going to solve this equation. So 80 times negative 3 is minus 240. And there we go. And then I'm going to divide both sides by negative 50. Negative divided by negative. So the acceleration of person B, I think we're just looking for the magnitude, but I can write it all down. Let's see, I take 240 divided by, or negative 240 divided by negative 50. I get 4.8 meters per second squared. And because I said positive is right, that means this person, and you can tell by my diagram, I think I did it the opposite in my note, but all I'm looking for here is the magnitude because I didn't specify directions. And so the person in B here, the smaller person, accelerates faster. And that is a big key with Newton's second law, F equals ma, is if the force is applied is the same, like in this situation, if your mass goes up, to balance it out, your acceleration goes down. Or the flip side is true, is that if your mass goes down, you're smaller, you're going to accelerate faster. So that's the relationship there. So when these two people push each other, they are not going to go out at the same speed because they have a different mass. And according to Newton's law, that will change their acceleration. Where this applies, well, if you're somebody who likes boating, I've seen this happen before where in a canoe, I watched somebody try to jump off a canoe into a dock. The problem was the canoe was lighter than them. And so when they pushed off, the canoe flew out one way. They didn't make it far enough to the dock, and in they went wet. All right, so you got to know Newton's third law if you're going to jump off a boat or a canoe. Make sure it's much, much bigger than you so it doesn't accelerate anywhere. That's why it doesn't bother you to jump off a great big boat, because it's only going to accelerate a small amount where you accelerate enough to jump onto the dock. All right, so that is, again, the start of our next part of the course, where we're going to look at forces today.